Hi, I am Bhushan Suwal, and I'm going to introduce GerryChain, a package I wrote with my collaborators Parker Rule and Matthew Sun at the Metric Geometry and Gerrymandering Lab at Tufts University. Here we apply tools from mathematics and computer science to study political redistricting. In American politics, the way district lines are drawn have a profound effect on voter representation. Gerrymandering is the practice of carefully constructing district lines to favor the voices of some voters over others. We have developed algorithms to flag potentially gerrymandered districting plans via ensemble analysis. This is the basic idea. Say you think a plan has been gerrymandered. What we can do with our algorithms is generate diverse ensembles of reasonable districting plans using Markov chains. Now you could compare the plan you have brought against this ensemble. If the plan is an extreme outlier, there is good reason to believe that something may be amiss. Our package GerryChain generates these ensembles. To do this, we typically use an algorithm we call ReCom, short for recombination. ReCom works by merging the graphs of two districts together, drawing a random spanning tree and cutting the spanning tree in half to form two new districts. We maintain a popular Python library called GerryChain that implements several flavors of ReCom. Under the hood, GerryChain relies on NetworkX, a graph library written in pure Python. We have found that calls to the graph operations in NetworkX are a significant bottleneck in our experimental workflows. We consider replacing it with a faster graph library within the Python ecosystem, but Amdahl's law suggests that due to the overhead of using Python in general, that it wouldn't help much. Porting our key graph algorithms to Julia then was a natural option. We designed and implemented a new library, GerryChain.jl, that has all of the core functionality of Python GerryChain. The process of rewriting the library in Julia was surprisingly straightforward, as the learning curve of Julia was not too steep. The speed of sampling ensembles depends on many different things, including the constraints, acceptance probabilities, and the number of scores we are keeping track of. Here we show the runtimes of two different types of Markov chains in Julia and Python. We found that, at least for simple chains, the Julia version of GerryChain was 47 times faster than the Python chain. This has drastic benefits, improving our research workflow by shortening the time to see results to minutes instead of hours. In conclusion, our package GerryChain generates ensembles of districting plans to compare a proposed plan against, and we do this using random walks on graph partitions. We have observed our implementation in Julia to be about 47 times faster than our Python implementation, and we have been thrilled by both Julia's ease of use and rich ecosystem of packages.